All right, welcome to our video today. It's going to be on force on a current carrying wire in a magnetic field. This is going to be a shorter video today, hopefully. I'm shooting for about 10 minutes here. We're going to be able to do two things by the time we're done watching this video. First, we'll be able to determine the force on a current carrying wire in a magnetic field. And then second, we'll be able to determine the total force on a current carrying wire on a loop in a magnetic field. Okay, definitely want to have your journals out at this point. Copy these things down, pause, go back through, make sure that you understand every step that I'm going through in these problems. So the first thing that we're going to look at is the force on a current carrying wire. Now, right here you see a wire, and it's in a magnetic field, and that magnetic field is pointed out. The current in this case is pointed directly straight up. And you can see that right here represented by that red arrow. Now, if this were simply a charge in a wire, we would know exactly what to do. We would just use our right-hand rule number 1 and solve for the direction on that charge. Well, it turns out that for a current-carrying wire, it's no different. In any current-carrying wire, there are charges flowing through the wire. We know that those charges are negative and flowing this direction, in the opposite direction of the current. However, we're going to pretend like they're positive charges flowing so that we can use a right hand rather than a left hand rule. So remember that we're going to imagine that the charges are positive charges flowing in the same direction as the current. So what we need to do is use our right hand rule number 1. So everybody follow along with me. Take your index finger of your right hand and point it straight up. Your middle finger, have it pointed out of the page or out of the screen at yourself. Your right thumb right now should be pointing directly to the right. So this current carrying wire is going to experience a force pointing to the right. Not so bad. Just do the same thing that you do for positive charges, but instead of your index finger being the velocity of the charge, your index finger is going to be the direction of the current. And this wire would move that direction. Okay, to the right. Now, what's a little bit more difficult is we can't simply use the equation that we have for force on a current carrying wire. FB equals QVB. Because simply we have too many charges flowing here. There are millions of charges flowing through this wire, not all at the same velocity. Some are moving faster than others as they knock along, going through the wire, so this equation isn't going to work. However, there is a separate equation, and that equation is the magnetic force on a current carrying wire in a magnetic field is equal to I, L, B, where I, of course, is the current, B is the magnetic field strength, and L is representing the length of the wire in the magnetic field. So in this case, L would be this length right here, measured in meters. This will give you the magnitude of the force, and don't forget to use right hand rule number 1 in order to determine the direction. Got it? So all we're going to do now is look at a simple problem using this and our idea of electromagnetic induction. This is a problem that I pulled directly from an AP exam that Noble students did take. I think there's some things that are easy about it and some things that are more challenging. The first question that we have is what direction is the current flowing through the loop as it enters the B field? So let's take a second and dissect this. If we look up here, what we have is we have a loop of wire, a single loop on a cart, and we know that that cart is going to be moving to the right into a magnetic field. Right now there is no magnetic field, but as it moves to the right, it's going to slowly enter that field until it enters completely. Again, as always, I think you should be more impressed by my ability to manipulate the smartboard for your educational purposes. Let's watch it again. So this is going to slowly enter the magnetic field. Now, the main thing that we're going to want to think about is flux through the loop as it enters the field. So right here, when we're outside of the magnetic field, there is 0 flux through the loop. But here, while we are inside the magnetic field, we do have a flux, and that flux is pointing inward. So we go from a situation of 0 flux on the left to there is some flux on the right. So that is an increase in magnetic flux inward. Now, if you remember, that loop is going to want to oppose the change in flux. So if there's an increase in flux inward, this loop is going to create its own flux outward. So we're going to use right-hand rule number 2. Everybody do this with me. Take the thumb of your right hand and point it outwards. Curl your fingers, and those fingers curl in the counterclockwise direction. So we know that the current is going to be flowing through this loop this way in the counterclockwise direction. So the answer to this question is counterclockwise. Oops-de-doo. Counterclockwise. There we go. Good. Well, we can be done with this question now. And let's look at secret hidden question number 2. What is the induced EMF if it is traveling at 3 meters per second? Well, we only have one equation that can work with this, and it's the idea that the induced EMF is equal to the change in flux over the amount of time that that flux changes. So, change in flux. There's no flux at the beginning, a lot of flux at the end, and so the change is simply going to be equal to that flux when it enters the magnetic field. That flux is equal to the magnetic field strength times the area of the loop. Now, the amount of time is a little bit trickier to get. What we have here is we know that the velocity is 3 meters per second, and we know right here that the length of the loop is 0.2 meters. So what we need to do is we need to use the equation x is equal to vt, knowing full well that there is zero acceleration, it's a constant velocity, in order to solve for the amount of time. That simply translates to position divided by velocity to get for the time, or to solve for the time, and we're set to go. So if we look here, we know that the magnetic field strength is 2 Teslas. The area of the loop is going to be 0.1 times 0.2. And then the amount of time needed is going to be 0.2 meters divided by the 3 meters per second. If you carry out that calculation, you should get 0.6 volts for the EMF. So I'm going to write that up here so that you remember that the EMF is 0.6 volts when this enters the loop right there. All right. Secret question number 2. What is the magnitude of the current flowing through the wire? Okay, we already know that the current is flowing through the wire in a counterclockwise direction. So what we should simply be able to do is use Ohm's law. V equals IR. We know that the voltage in this loop is 0.6 volts, and we know that the resistance is 40 ohms. If you plug that in, you end up getting a current that's equal to 0.015 amps. So far, none of the calculations have been hard. The ideas using right-hand rules, the idea of flux, are where the complication lies in this problem. But if you have some basic understanding of flux, you should be able to get the correct answer. Now let's look at the last question using the equation that we just learned in the right-hand rule. What is the net force on the wire once it has completely entered the magnetic field? Okay? Well, so what we need to do is we need to look at every single section of this loop right here once it has entered the magnetic field. So let's look at the right side first. We know that the current is flowing upwards, so we're going to use our right-hand rule, number 1. Everyone do this with me. Make the right-hand rule shape with your right hand. Take your index finger, point it straight up, your middle finger pointed into the screen, and what you should see right now is that your thumb is pointed to the left. That's right, it's pointed to the left. So we know that on this side we have a force pointed to the left. Let's do the top. We know that the current is pointed to the left. So take your index finger, point it to the left. Your middle finger should still be pointed in, and we get a force that's pointed down this direction. If you go to the right side, we're going to follow that same procedure. You end up with a force that's pointed in. If you go through the bottom of the loop this direction, use the same right-hand rule, you get a force that's pointed up. So what you should notice here is that we have 4 forces, all pointing opposed to each other. And since the current is the same, these forces are going to all cancel out. So we get a net force in this case, which is equal to 0 newtons. Once it is in the loop, once it's in the magnetic field, this loop should no longer field any force in any direction, and it'll move along at a constant 3 meters per second. All right, not so bad. So pause, take a look back, see if you have any questions, and we'll see you next class.